Welcome to another podcast. In this episode, we're going to be taking a look at electrical circuits for the first time this semester. Give you a little bit of background information on them for those of you that may not have been exposed to them in your physics courses. You're not going to need to know a ton about electrical circuits or electricity this semester, although we will talk about electricity and magnetism a little bit, especially in the PDE's course. But I'll try to fill you in on most things as we go along. So pictured here to start with is what is called an LRC circuit. And just to familiarize ourselves with the terminology a little bit, L stands for inductance. It's measured with units called henries. The capacitor is C. Capacitor is measured in a unit called Faradays. The R stands for the resistor, and it's usually measured in ohms. Capital Omega there for the unit definition. E is the voltage source or the electromotive force. And the idea is across each of these is something known as a voltage drop. In other words, what happens is the voltage source sends out an electrical current. That current travels across the inductor, which is usually a coil, the capacitor, which is usually two metal plates close to each other, and then the resistor, which usually is, it can be a lot of different things. Sometimes it's just a feature of the material the circuit's made out of anyway, but it's a resistance to the flow. At each one of those stops, you lose a little bit of that voltage. And so the voltage drop for each of these can be measured, and that's a specific law. We'll start, for example, with Faraday's law. Faraday's law measures the voltage drop across the inductor. The voltage drop across the inductor is proportional to the rate of the current. And so it's just the inductance times the derivative of the current with respect to time. That's the voltage drop in that case. For the capacitor, I need to introduce one more variable here. I is the current, and Q is the charge in this case. Voltage is, I guess, the other thing we'll talk about here. Voltage is measured in volts. Current is measured in amps. So those are some of the basics terminology-wise. In terms of the capacitor comes from something called the capacitance law. The capacitance law states that the voltage drop across the capacitor is inversely proportional to the charge. And so basically what you're going to take is the capacitance, 1 over C, times the charge. And that is the voltage drop. So the resistor in this case is something called Ohm's law. Ohm's law states that the voltage drop is directly proportional to the current. And so those are the three voltage drops that we need to be aware of, at least telling us what happens across each of these objects. Now, to get this to be a differential equation, like we had a balance law for the mixing problems, we also have a balance law for electrical circuits. And the balance law for electrical circuits is something known as Kirchhoff's law. And let's see here. Kirchhoff's law does have two H's. I always forget if it has two H's. Two H's and two F's. So Kirchhoff's law. Kirchhoff's law states that the sum of the voltage drops across a closed circuit are equal to the voltage source. Now, if we apply that in this case, what it gives us is the following equation. The sum of the voltage drops is L times di dt, that's the voltage drop across the inductor, or the coil, plus the voltage drop across the capacitor, which is 1 over C times Q, plus the voltage drop over the resistor. All of that's equal to the voltage source, which is E of t. The voltage source is a function of time, as is the current, as is the charge. So L, R, and C, at least for us this semester, are going to be constants. But I, Q, and E are all functions of time t. Now, because of that, we have this equation, but it's really not in a great form yet. So there's two different ways you can go about it. You can find the current equation. So if you want to solve for current, the current equation, you find that by taking the derivative with respect to t of each of these pieces. So notice here, if I take the derivative with respect to t, that's two derivatives now, plus 1 over c times the derivative of q, plus r times I, the derivative there. I'm just taking the derivatives of the pieces with respect to time. So L, C, and R are not functions of time. They're constants, so I can avoid them when I take the derivative. And that's equal to E prime. Now, there is one little sort of side note here, and that's the relationship between I and Q, between the current and the charge. It's important that you know that current is always equal to moving charge. What that means is that if I have the derivative of charge, that is current. And that's important here because I have the derivative of charge right here. So I can replace that with I. And in doing so, what you notice is I have a differential equation, but it's a little bit different than the differential equations we've seen so far this semester. The differential equation in this case involves a second derivative. It's the first one of these we've seen this semester. This is a second order ODE. Because it's second order, we don't have the tools to solve it at this point. However, there are circuits that we can solve, and those circuits are RC circuits or LR circuits are the two most common types. For example, in an RC circuit, you don't have L, and so you would forget about L. And in an LR circuit, basically you would solve for it in terms of the charge rather than in terms of the current and look at the equation in that case. But we're going to be mostly concerned with an RC circuit in here, and because of that, we're going to be solving the following differential equation several times here over the first month of the course. And so it'll be Li prime plus Ri equals E. So this is an LR circuit. Just coming back up to this equation right here, where we forget about the capacitance. The capacitance is no longer part of the problem, so I don't have a voltage drop there. And so that's an LR circuit, and then an RC circuit would be very similar as well. But these are the types of circuits that we're going to talk about this semester. And I just wanted to give you a little bit of background information about where they come from, what are some of the terminologies that I'm going to be using in class. You definitely want to read about this in your textbook. It's in section 3.4, so spend a good bit of time reading about the derivation of these electrical circuits. All right, thank you for watching.